Humans have the ability to adapt their thinking and reactions to different situations, conditions in neural networks. But machines do not. Regardless of the type and complexity of the samples presented, they systematically perform the same function. To solve this problem, researchers used adaptability, and it led to the development of AdaTape. Imagine a machine learning model that works harder on difficult tasks and adapts its approach to task complexity. Hang in there, you are going to witness the wonders of AdaTape. AdaTape is a new entry-level model by Google that uses adaptive computing and dynamic reads and writes to achieve peak performance across a wide range of tasks. It is particularly useful for tasks that require the model to handle complex or noisy inputs, such as natural language processing and machine translation. Adaptive computing refers to the ability of a machine learning model to adapt its behavior in response to changes in the environment. In the context of AdaTape, this means that the model can dynamically decide how many calculations to perform for each input, depending on the complexity of the input. This makes it more efficient than traditional based models that have to do the same amount of calculations for all inputs. So, let us make a comparative study between adaptive computing and traditional neural networks. Traditional neural networks, the foundation of modern machine learning, have historically taken a rigid approach to tasks. Whether it's easy or hard, they make the same effort. But the world is not that simple. Some tasks are inherently more complex than others and require different levels of attention. Adaptive computing fills this gap. Adaptive computing, a dynamic approach to machine learning, allows systems like AdaTape to adapt their operational strategies to the complexity of the task at hand. Unlike traditional models that treat all tasks the same, adaptive computing scales its effort based on complexity, resulting in more efficient and accurate results. In contrast to traditional neural networks such as T5, GPT-3, PaLM, and ViT, whose computational budget is constant from sample to sample, recent research has shown that adaptive computational budgets can improve the performance of tasks where transformers fail. Much of this work achieves stability by using dynamic depth to allocate computational budget. For example, the ACT, Adaptive Computation Time algorithm, has been proposed to provide an adaptive computation budget for recursive neural networks. Universal Transform extends to the ACT algorithm to transformers, making the computational budget dependent on the number of transformer layers used for each input, sample, or token. Recent research, such as PonderNet, takes a similar approach while improving dynamic shutdown mechanisms. Adaptive computing in neural networks is interesting for two reasons. First, they offer an inductive bias that allows different numbers of computational steps for different inputs, which can be crucial for solving arithmetic problems that require modeling hierarchies of different depths. Second, it makes it easier to adjust inference costs due to the greater flexibility that dynamic computations offer, since these models can be modified to handle multiple flops with new inputs. Dynamic reading and writing refers to the ability of a machine learning model to selectively read and write information to memory depending on the task at hand. In the context of AdaTape, this means that the model can only read and write information that is relevant to the current activity. This makes AdaTape more accurate than traditional entry-level models that must read and write all memory inputs. It outperforms the main base models in a variety of ways. First, natural language processing. AdaTape performs best in the GLUE benchmark, a series of natural language processing tasks. Second, machine translation. AdaTape performs best in the WMT benchmark, a set of machine translation tasks. Third, captions. AdaTape scores highest in the COCO benchmark, a series of captioning tasks. Let us get into the intricacies of this new AI. How does it work exactly? AdaTape is very easy to implement, as it directly allows adaptability to input sequence rather than pattern depth, and it is also very accurate. AdaTape uses an adaptive tape playback mechanism to determine the different tape tokens to add to each input based on the complexity of the input. AdaTape is a transformer-based architecture that uses a dynamic set of tokens to create a flexible input sequences. AdaTape uses adaptive functionality. It also uses vector representation to represent each input to dynamically select a sequence of resizable chip strips. The AdaTape uses a bank of tapes to store all potential tape tokens, which interact with the model via an adaptive tape playback mechanism to dynamically select a sequence of resizable tape tokens. The researchers used two different methods to create a stripe bank. First, an input-driven bank. Here, an input-driven bank extracts a bank of tokens from the input, using a different approach than the original tokenization model to map the raw input into an input sequence of tokens and a trainable bank, wherein a more general way to generate a streaked bank using a set of trainable vectors as streak tokens. The decisive advantage of AdaTape is mind-boggling. Here are some advantages of using AdaTape with emojis. First, it is known for greater efficiency. AdaTape can be more efficient than traditional entry-level models because it only performs a number of calculations required for each input. This can be a significant advantage for complex or resource-intensive tasks. Second, for its greater accuracy, AdaTape can be more accurate than traditional base models because it only reads and writes information relevant to the task at hand. This can be a significant advantage for tasks where the model needs to process a large amount of data. AdaTape redefines performance by offering a dial that increases accuracy while maintaining performance compared to other adaptive designs. By manipulating tape tokens, AdaTape can achieve higher accuracy with minimal cost, increase and vice versa, depending on the desired outcome. Third, it has greater flexibility. AdaTape can be more flexible than traditional base models because it can dynamically adapt its behavior to different inputs. This can be a significant benefit for tasks that require different types of input. Unlike its counterparts, AdaTape maintains its stability by sticking to a fixed number of layers. This strategic move eliminates memory and speed complications and differentiates it from models that dynamically adjust their fill levels. And you know how efficiently it works? The exceptional performance of the AdaTape is highlighted by specific tasks. Partly problems in which it determines the even or odd parity of binary strings demonstrates its ability. In addition, AdaTape avoids the pitfalls of models that select specific components based on input data, thus ensuring efficient optimization of all parameters. What sets AdaTape apart is its ability to successfully handle a variety of scenarios. Whether it's image classification, algorithmic tasks, or natural language understanding, AdaTape always delivers excellent results. AdaTape's performance shines when it comes to image classification, allowing you to achieve the highest level of accuracy with minimal processing power. For example, in the ImageNet 1K dataset, AdaTape achieves an impressive top 1 accuracy of 83.8% with only 86 million parameters and a 4.5B flop, outperforming models like VIT and DIT. AdaTape's capability also extends to algorithmic tasks, showing excellent performance on tasks such as addition, multiplication, sorting, and parity. AdaTape is very easy to implement and provides an effective slider to increase accuracy when needed. But it is also much more effective than other adaptive baselines because it introduces adaptability directly into the input sequence and not just into the depth of the model. Finally, AdaTape offers better performance for standard tasks like image classification and algorithmic tasks, while maintaining a good compromise between quality and cost. The score highlights AdaTape's intelligence as it can effectively identify and prioritize the most informative patches to improve its performance. Now, having researched decently into the topic, we will look into the success rate of this. Researchers tested the usability of AdaTape on various parameters. They found that all repeatability parameters were exceeded in the input selection mechanism and provided inductive biasing that allowed implicit meter maintenance not possible with standard transformers. Researchers also evaluated AdaTape on image classification tasks. They tested AdaTape on ImageNet 1K and found that AdaTape performed significantly better than alternative basic adaptive transformers in terms of the trade-off between quality and cost. AdaTape Google AI represents a milestone in AI computing. It has the potential for increasing the problem-solving potential and quality of image classification. AdaTape's innovative approach has the potential to transform the AI landscape by providing industries with flexible and powerful models that will revolutionize the impact of AI-based solutions on the market. We really hope that you, the new model AdaTape, can solve real-world problems in the future. AdaTape is a pioneer in adaptive computing. Its transformative approach to adapting strategies based on complexity paves the way for more efficient, accurate, and comprehensive machine learning models. Moving forward, AdaTape's impact on various tasks and benchmarks promises to redefine the boundaries of what's possible in the world of machine learning. In the meantime, we are on the hunt for the next big AI reveal in the world. Check back to our channel to be updated. Thanks for your time. Support us by subscribing to our channel.